Słyszysz mnie? Cześć, witam Was bardzo serdecznie na czwartej edycji Meetupu DevOps po godzinach. Ja jestem Andrzej Kiesz, jestem jednym z założycieli InfoShare Academy. Słuchajcie, dzisiaj tematem przewodnim będzie Apache Kafka. Nasze prelekcje dzisiaj będą w języku angielskim. Wystąpią dwaj bardzo, że tak powiem, mocni zawodnicy, panowie, którzy obaj pracują dla firmy Confluent i są mega ekspertami w dziedzinie Kafki. Dzisiaj będziemy mieli dwa wystąpienia. Pierwsze wystąpienie takie wprowadzające do Kafki, Introduction, Overview and Use Cases. Wystąpi na początku Sven Erik Knop, natomiast drugie wystąpienie będzie na temat tego, jak Kafkę utrzymywać, jak automatyzować utrzymanie Kafki, jakich narzędzi użyć, i wystąpi Pere Urbón-Bayes, również z firmy Confluent. Zanim przejdziemy dalej, kilka informacji organizacyjnych. Te wystąpienia będą w języku angielskim, ale mamy nadzieję, że dla Was nie będzie to żadnym problemem. Jeżeli chcecie nagrania, bo z jakiegoś powodu nie będziecie mogli uczestniczyć w całym webinarze, no to po prostu zostawcie nam swojego maila, zapiszcie się i na pewno po zakończeniu webinaru wyślemy Wam linka do nagrania, tak abyście niczego nie przeoczyli. Druga sprawa jest taka, że w trakcie tego webinaru, w trakcie prezentacji możecie w komentarzach zadawać pytania. Postaramy się na te pytania odpowiedzieć na końcu każdej z prezentacji, ale na końcu mamy również przewidzianą sesję Q&A, pytań i odpowiedzi, więc na pewno żadne z tych pytań nie będzie pominięte, dlatego nie bójcie się, nie zastanawiajcie się, po prostu pytajcie, jeżeli macie jakieś pytanie do tego, co aktualnie jest omawiane, po prostu wrzucajcie w komentarzu i będziemy odpowiadali albo po każdej prezentacji, albo na końcu w sesji Q&A. Słuchajcie, partnerem naszego meetupu jest firma Intel, za co bardzo dziękujemy, natomiast naszymi community partners są konferencja InfoShare, konferencja Future Fee, o której zaraz powiem kilka słów, oraz seria meetupów Tech 3 Camp. No właśnie, konferencja InfoShare F3, czyli nowa odsłona Future Free, które jeszcze niedawno były targami pracy, teraz jest to już konferencja z kilkoma ścieżkami tematycznymi. Ta konferencja odbędzie się w sposób stacjonarny 19 maja, w czwartek, już niebawem, na Ergo Arenie w Trójmieście. Dokładnie Ergo Arena jest na granicy między Sopotem a Gdańskiem. Serdecznie zapraszamy. Udział jest bezpłatny. Wystąpią bardzo fajni paneliści zarówno z Polski, jak i z zagranicy. To są nazwiska, których nie musimy Wam przedstawiać, ale wejdźcie sobie i zobaczcie, jacy będą prelegenci. W komentarzu powinien pojawić się już link do tego wydarzenia. Tam zobaczcie sobie listę prelegentów. Myślę, że warto, nie tylko dlatego, że będą fajne wystąpienia, ale dlatego, że jest to, no, w końcu rozpoczyna się ta seria stacjonarnych konferencji, meetupów, więc można w końcu przybić piątkę i porozmawiać live, a nie tylko patrzeć na webinary. Także zerknijcie, udział jest bezpłatny, są oczywiście też bilety płatne, ale cały przychód jest przekazany, będzie przekazany w celu pomocy osobom na Ukrainie. Także zerknijcie, myślę, że warto. Jeszcze jedno słowo na temat kursu DevOps. Gdybyście byli zainteresowani wzięciem udziału w naszym kursie DevOps od podstaw, który organizujemy, i kolejna edycja wystartuje 23 sierpnia, to również Was serdecznie zapraszam. Z kodem DevOps po godzinach otrzymacie 500 zł zniżki na ten kurs. Ok, słuchajcie, wracamy do naszej głównej tematyki, czyli do Kafki. To będzie w języku angielskim, dlatego ja teraz przełączam się na język angielski. So now I'm switching into English. The first presentation will be given by Sven Erik Knop, and he will tell us more about the overview, the use cases, and will give us the general introduction about the Apache Kafka. Hello, Sven. Could you please join us?
Hello. And thank you very much for the introduction.
Okay, Sven, it's very nice to have you here with us. And I think the mic is yours. So please start your presentation right now.
Fantastic. Thank you. So, as Angela said, my name is Sven Erik Knop, or Sven, very simply. I am a senior solutions architect and team lead at Confluent. My role is being an architect, developer, presenter, and team lead. I've got many hats on. and you can reach me on Twitter at Sven Erik Knop. I've been with Confluent now for 4 years, moving up as a standard solutions architect to then being promoted to a senior solutions architect and now team lead. But who is Confluent? Well, Confluent has been created in 2014 by the original creators of Kafka. They used to work for LinkedIn, created Kafka there for reasons I will explain in a second, and then decided to make themselves independent, create a company to follow on Kafka because LinkedIn themselves were not interested in that. Confluent these days is headquartered in Mountain View, used to be in Palo Alto. Our mission is to build an event stream platform, or the notion now is data in motion. And yes, we are hiring, still hiring, despite the fact that we have grown quite tremendously since I joined. Why use Apache Kafka? If this picture here looks familiar to you, you might have been starting with microservices. That certainly was a picture at LinkedIn in 2010, around that time, when they started to move their more monolithic applications into microservices, and then had lots of different services flying around that were trying to communicate with each other with databases, writing to log files, running matrices, and so on. But there was no common way to do that. So each particular service had their own way of doing this. It became very quickly very chaotic, or spaghetti-like, as you can see here. The solution for that, as defined by Jay Krabs and his team, was to create a common platform, a common streaming platform that sits in between that and connects all the services together without tightly coupling them. They're loosely coupled through that service, through the streaming platform. And that makes it possible through the fact that it's a low latency kind of environment to fulfill all the requirements we have with the different services. What is Apache Kafka? I've given this presentation about 3 years ago in Gdansk when InfoShare was still doing this publicly, and hopefully we'll do that again so we can meet in Gdansk or other places. And when I asked this question in the room, what is Apache Kafka? One of the typical answers I got was, well, it's a publish subscribe queue, right? Well, not quite. Things like MQ Series or ActiveMQ or RabbitMQ or something like that, they are traditional publish subscribe queues. Kafka can do that, but that's not what Kafka is. Okay, it's an event streaming platform. You just said so. Well, yes, that's what this goal is, but it's not what Kafka is. Is it a database? Can be used as a database in many cases. But the actual nature of Kafka itself is a distributed immutable log. What does that mean? Well, a log is traditionally a file to which you append at the end. It's the fastest possible operation when you deal with a file. So Kafka is always persistent. It is distributed because there are typically multiple components involved, and therefore it is fault tolerant because if one service goes down, the other services will take over its role. How this all happens, we will discover during this short lecture. So let's produce this log. What does that mean? Well, there's a file and we append messages, events, something like that to the end. They are ordered implicitly in time. One event that comes in later will be appended further down in that particular log. We call this log a topic. Now, I was trying to find an analogy for that, and the only one I could come up with is a stock ticker. You might have seen a device like that in the museum. They were connected to a telegraph, written to with a bit of fantasy, an endless tape to write the messages down. They're certainly immutable. You don't go back and forwards. You just append at the end. Good. What are we going to do with that? What are the consequences of this? Well, if we want to read again from this topic, then we need consumers. These consumers, all they need to know is which topic do we read from and where we are within that topic. And each consumer can keep track of that themselves. This is the so-called offset. So all I need to know is where am I on this particular tape, on this particular topic, and I can read from that. Several consumers can do this independently of each other. The broker is the service that Kafka provides and sits on top of the topics, doesn't need to know with the consumers where they are. The consumers can regulate themselves. These consumers are independent of each other. And they will be running at different speeds. There will be consumers that are trying to keep up with the log, with the topic, as quickly as possible to keep low latency, trying to process the messages as soon as they come in. There will be other messages that take a little longer time. That have to processing. They might have to do some double checking by going to other services and reading the information from a database or a REST interface or something like that, or doing complex calculations. So they might take longer. And there are other consumers that will start up a later time. They might read from the beginning of the log, from the topic, because they just trying to populate the cache and tries to keep all the data up there. Again, with the analogy of a stock taker, I found this picture. So these ladies here read from the log, read from the messages, independently to different consumers, and then do something with that. For example, updating the spreadsheet or the board in the background with that. And with a little bit of fantasy, with a bit of imagination, you can even see that the log doesn't go on forever, and at one stage it will be thrown away. It winds up in the bin here. We call that the retention. After the retention period, we'll throw this thing away. That is as far as I want to stretch the analogy with the stock taker. We'll leave it at that. Good. Now we're going to look at some of the consequences. So we're trying to scale this up. I said Kafka is scalable. If we want to scale this up, then we have the problem that our producers might overwhelm the Kafka broker, because we are trying to push more data down into the Kafka broker than we can possibly write to disk. Now, Kafka itself doesn't flush the disk, but it will let the operating system do that. And once the buffers are full, we have to write out. More commonly, the problem is that a consumer might have trouble catching up with the producer. Why would that be? If you just measure it out, the producer itself is typically slower than the consumer, because the producer has to eventually write to disk. There is a limit in there how many megabytes per second we can push through. A consumer will typically read from cache, because the file system cache, so it'll be much faster to read that. It is what the consumer does with the messages that is the reason why the consumer might be slower. So if I need to process data, I need to aggregate information over a certain period of time. If I have to go and do lookup, comparison with the values, would I find that particular user that comes in? But if there's clickstream messages coming in, I might have to look up the user in a database or somewhere else. And these processes might take a longer time. So therefore, the consumer might be slower than the producer. And if that's the case, well, then we have we have a high latency. We might have a very tight SLA of saying within 100 milliseconds we have to be able to process the message, and if it takes several seconds, then we have a problem. Even worse, although I give the topic theoretically infinite size, in reality there are limits. In reality, the Kafka broker will throw away messages after a certain period of time, by default 7 days. If the consumer is that slow and hangs behind that bunch, then we are on the risk of losing messages themselves if we extend the retention period before we read the messages, because there's no back pressure on the producer. There can be multiple consumers working on that. Producer doesn't know anything about the consumer, might be struggling, so it just keeps on producing. So for all these reasons, we need to find a way of scaling this out. And the standard way of doing that is to shard the data, spread it over multiple partitions, as we call it. So a topic typically is spread over multiple partitions. If we do this, then we can, as a producer, simply write the messages down into each individual partition of that in a round-robin fashion. The problem with that, of course, is that we now lost the ordering. Because we're writing to multiple partitions in an arbitrary, effectively arbitrary way, the consumer will not necessarily read them in the same way down. Consumer typically reads a batch of messages, so it gets a whole buffer full of that, and it will do that in different order than the producer writes to it. So I have now guaranteed that the order is preserved. What if the order is important? Well, often the order is not important for the whole topic, but only for a subset identified by a key. So in Kafka, I can write the messages down with an optional key. If you don't provide a key, then the producer library will automatically pick the right partition for you and will go round robin. But if you provide a key, then by default, the producer will take that key, we'll calculate the hash from that to have a reasonably good distribution about it, and then take a modal operation of the number of partitions and define the partition that way. And so we guarantee that for the same key, we'll write to the same partition. And therefore, all messages with the same key are ordered. That has a couple of consequences. First of all, we need to pick the correct key. So I've seen that some customers of ours have used a timestamp or UUID or something like that as a key. These are the worst possible keys you can imagine, because they have no purpose for this particular to pick up the right partition. They are by nature not repeatable, so you never find the same key again. So there's no ordering guarantee in that. There's simply no point of having this kind of key available. A good key is something like a customer ID or a product ID or a sensor or something like that. Something identifies messages where you want the things to be in order. That's a good key. The other consequence of this is that the number of partitions is static. We define this when we create a topic, and we typically don't want to change this. So if you changed the number of partitions for a topic, then the next message with the same key would potentially wind up in a different partition, depending on what the hash key calculation gives us. The modal operation will be different. It is possible to change the number of partitions for a topic, but this is more typically a quite expensive operation. You either have to drain the topic completely of messages before you change the setting, or you have to kind of reroute the messages to another topic with a different partitioning scheme. And then when the old topic has been expired, then retention has removed it, you can then swap back over again with the old name. So it's important when you create a topic to create it with a good value for partitions. What's a good value? Well, think of it how much slower your consumer is than your producer. If you think you will need 10 consumers in order to process all the messages in parallel the producer sends in, well, 10 partitions might be a good choice. But typically what we recommend in this case is to over-partition by, say, a factor of 2. So if you have, if you calculate that you might need 10 partitions, you might well make it 20 partitions so you have some leeway. Why? And how does it actually work with the partitions and the consumers? Well, we have to understand the concept of consumer group. As I said before, consumers are independent of each other. They do not share the offset. They just simply work independently on that. In order to bring them together, we need a consumer group. Just simply group together by using this group ID. That's a string inside the configuration of the consumer. All the consumers of the same group ID are coordinated together. They will share the partitions of a particular topic among them, so that each partition is assigned to exactly one consumer. One consumer can have more than one partitions assigned to it. If you start with one single consumer in the consumer group, then all partitions are assigned to that. And as you increase the number of consumers, then dynamically we will reassign the partitions to the consumers on that, and stop the existing consumers, and then reassign them again. What happens if we lose the consumer? So here again, just for simplification to avoid the number of arrows in this picture, partition 0, 1, and 2. If I lose a consumer, then the partition that's been assigned to that particular consumer will be reassigned to another consumer. So I can dynamically dial down the number of consumers I have running, and the other way around, I can also bring new consumers up. So if I over-partitioned, if I said I have, let's say, 10 partitions in my topic, and I'm running 10 consumers at the moment, 5 consumers at the moment, and then I find that the consumers are struggling with the throughput, so the latency goes up, we're lagging behind, then I simply add more consumers to it. They will join the group. There will be a repartitioning event or a reassignment event, and then the overall number of partitions per consumer will drop, and therefore the consumers can deal with the load, and my system is stable again. So that's how partitioning works with Kafka, and that's how we scale our producers and consumers and scale our topics by just sorting the data across, typically with a key if you have a key available. If you don't have a key available, You can still do this, but obviously then you have to be aware that the ordering is, in this case, is lost, which might not be a problem for you. Okay, how can I make this resilient? So we talked about scalability, but now we have resilience. Resilience builds multiple instances. So a Kafka broker, generally, a Kafka cluster consists of multiple brokers. Brokers are the instances, the binaries that actually look after the topics. In this example, you have a cluster with 4 brokers in. They have a broker ID. And when I create a topic with multiple partitions, it will be spread across those brokers. This is actually an accurate picture of what happened if you created a topic with 4 partitions and you have 4 brokers. They will be spread this way. For each partition, we'll have a leader. A particular broker is responsible for that particular partition. The leader is the one single instance that all the consumers and producers will talk to, and I will show you a picture of that in a moment. And we have followers. They pick up the data from the leader and store it internally as well, so that we have a multiplication of this data. The idea is, in this particular example, I have a replication factor of 3. That means the data is 3 times replicated. It's not one leader and 3 followers. It's in total 3 brokers have the data in them. And if I lose a broker, then another broker has to take up the slack. It has to become the leader. But how do we know whether that's eligible to be the leader? Well, with that, we have to think about the concept of ISR, in-sync replicas. So, in general, a producer and a consumer, the producer and consumer will always talk with the leader of a partition. If you know Kafka a little bit already, you might be aware of the fact that consumers can now be configured to talk to a follower as well, using the observer pattern, useful for multi-region environments. But if you don't do anything special, producers and consumers will always talk to the leader of the partition. What the producer will do depends, or how long the producer will wait for the message, but depends on its AX value, the acknowledgement value. By default, that used to be 1 up to Kafka 3.0 and now changed to all. What does 1 mean? Well, that means the producer sends a message to the leader. The leader puts a message into its own buffer, ready to be flushed down to disk, and then sends the acknowledgement back and says, dear producer, I have got the message saved. You can send another message. And the producer is then free to send another message as well. If I switch to AX equals all, which we always recommend, and which is now the default since Kafka 3.0, equivalent to Confluent 7.0, then all the followers have to also pick up the message from the leader, and they have to send an acknowledgement back to the leader and says, yes, you can forward the message now, or forward the ACT to the producer. So we're waiting for all of these additional brokers before we can send the next message. The consumer simply picks it up from the leader itself. Now, one of the consequences of this architecture is that if you have many, many brokers around, you probably don't want to increase the replication factor. If you 6 brokers, replication factor of 6 means that we'll have to wait for all the different constituents, all the different followers to be able to pick up. That's not very effective. That actually is quite slow. So in all our setups, we typically have a replication factor of 3 as the recommendation, especially if you put all the 3 different brokers in 3 different availability zones, or different data centers, and stretch it out across that. Even the loss of one data center, one availability zone, means continue to work. So what happens if one of these producers or one of these brokers goes down? This can always happen. It's a distributed system. For whatever reason, you might have to do a rolling restart with the brokers. You might do an upgrade. You might do maintenance. It might run out of memory, or whatever reason. There are some reasons that a particular system will go down. The design goal of Kafka is that the producers and consumers are none the wiser. They can continue to work, even if one broker is gone. So they have to be redirected. What actually happens is that the producers and consumers, even though I just connected them to the leader, will automatically be connected to all the other brokers as well. One of the first messages to get back from the broker is a metadata package that contains all the involved brokers, and it will connect to all of them so that the failover can go seamlessly and quickly as well. So if I lose broker number 1, I'll get the message to the producer that says, from now on, please talk to broker number 2. Fine. So from now on, I can use the broker number 2. But hey, why is broker number 2 suddenly the leader? Well, we have to guarantee that it has all the messages in it. Otherwise, the consumer lost messages. And we will only pick broker number 2 as being the new leader if it has all the messages in it. We call that being in the ISR list, in the in-sync replica list. So only a broker that can be is in the in-sync replica list, meta information that we keep up to date all the time, is eligible to become a leader unless we option in a special option that says we allow unclean leader election. But we typically run through mechanisms because you basically said you don't care about data. You're happy to lose some data potentially as well. Right. But there's another catch here. We only have 2 brokers left. Now we have a guarantee that we say 3 brokers are supposed to be able to be involved in the transaction, in the replication process. And we can't fulfill that because we don't have 3 brokers left anymore. To create a balance between availability and correctness, we added another parameter called the min in-sync replicas list, which down here is set to value of 2. Typically it is the replication factor -1. So if you have full replicas, then you would typically set the min in-sync replicas to 3. So in this case, we say, if a broker is unreachable, then we will accept a lower number of replications and still acknowledge to our producer that we have all the data in place. Okay. And that is the typical Kafka setup that you have in Kafka brokers, even for massive systems. You have 3 brokers, well, you have 3 brokers, the replication factor of 3, because typically they are much, much larger clusters than this. With the min in-sync replicas of 2, that means you can always always safely lose 1 broker for a period of time when the broker comes back on again, and then it will catch up the messages first until it rejoins the ISR list, and then the whoever will know that someone will assign it back to the partition and become back the leader again. Otherwise, after a while, all the leadership would wind up in 1 single broker. Doesn't make sense. So the leadership is sticky. It gets reassigned again when the broker is back on again and has caught up. So who decides which broker is supposed to take over? Well, this is the role of the controller. One of these brokers in here will be the controller. That decides which broker will be the leader of each particular partition. That's informed that a broker is down, and therefore then start the reassignment process. And how do we decide what the broker is? The controller. That's the magic of Zookeeper. So you might have heard that Kafka relies on Zookeeper for this kind of thing. You might have also heard that there's this KIP 500, KIP for Kafka Improvement Process 500 out there that says you want to get rid of Zookeeper. I mean, a little secret. I joined Confluent 4 years ago. And the very first day I walked into the office there, I very proudly announced to my colleagues that I had read the Zookeeper manual already from back to front, front to back, actually. And therefore I knew everything about Zookeeper. And they all looked at me aghast and said, "Why do you bother? Zookeeper's going away." Right. This is pretty much exactly 4 years ago. And Zookeeper is still there, alive and kicking. Yes, KIP 500 is in process. The latest versions have already built the infrastructure without Zookeeper in it, but it's not complete yet. And it will take probably realistic another year before Zookeeper is really gone. So for now, Zookeeper is still there and it runs a separate cluster. So how does Zookeeper work? Zookeeper is a quorum-based. It is a glorified key value store where the keys are stored in a tree kind of structure. And in the quorum, the majority has to agree on the state of the world before they accept it. Quorum, for this case, majority means for 3 Zookeepers, 2 of them have to agree. So you can lose 1 and you can still continue to work. If you have 5 Zookeepers, then you can lose 2 and you can still continue to work because it's more than the majority. So it should always be an odd number. And how many zookeepers you want, that depends entirely. Well, it's a discussion between you and your salesperson, who will tell you that you have the minimum of 5 zookeepers or even more than that, because they get money for that, for each node. If you very quietly talk to a professional services consultant like us, they'll probably say 3 is enough. Mark 5 and maximum if you're really paranoid. Good. So Zookeeper is used for 2 things in Kafka. One of them is a metadata store. So many things are stored in there that the Kafka brokers themselves don't want to store in their own structure to make sure that they're distributed correctly. This is one of the reasons why it took so long to get rid of Zookeeper, because we had slowly had to migrate the storage of the metadata into the brokers themselves. There are no living topics, many of them, but not all of them. So there's still work to be done. The other thing is that the data is stored, as I said, in a tree-like structure with different nodes, key value pair, and the nodes come in 2 types: static nodes and so-called ephemeral nodes. Ephemeral nodes that are going away, they need to be kept alive. The broker does that via a heartbeat. So it sends a regular message to the zookeeper, I'm still alive. As long as that's the case, zookeeper will happily declare that broker is still available. It is only when the heartbreak fails to come in that zookeeper will then inform all the interested parties, i.e. the controller, this broker doesn't respond, it seems to be dead. And then the controller goes to process and moves all the leaderships of the partitions that the broker served before to another broker. So what happens if a controller goes down? Well, then another broker will pick up. As soon as all the brokers are conformed that the controller is gone, each of them will vie to become the controller by setting this yet another ephemeral node with the controller node. And whoever's got the first puts his ID in there and it's then the controller, or everyone else just picks up information and says, okay, number 4 is the controller now. So this is the basic architecture of Kafka. We have brokers in a cluster. Each broker has a list of topics. The topics are broken down into individual partitions, be it 1 partition, be it 100 partitions. They work together with Zookeeper to keep information about whether a particular node is down or not. Producers and consumers talk to the leaders of each particular partition, and the producers are responsible for defining how accurate they want their data to be with the X value to get the data out. Let's talk about some use cases. What do you use Kafka for? This is the symbol for Kafka, by the way. Well, I call this the gateway drug into Kafka. Pull data out of a database, which might well live on some legacy system or a mainframe or something like that, and put them into a data sink. These mainframe systems are amazing machines to deal with transaction processing and so on at very high speed and very secure, but they're absolute rubbish as a cache. And in the times of internet where hundreds of thousands of people trying to access data, that's not very good. So more often than not, use something like Kafka to pull the data out and then write it into some front-end cache, or MongoDB, or Elasticsearch, or an S3 bucket or something like that in there. And often you try to massage the data in between. So the whole thing's called ETL, extract, transform, and load. That's quite a common use case. I might be connecting IoT devices. So you'll be amazed at how many sensors actually send the data to Kafka. Often not directly, often use the intermediate protocol called MQTT or something similar to that, which will is more valid for loose connections where you can easily lose connection. You can imagine that if you run sensors in a car, there are these days thousands of sensors in the car, even though mobile phone connection to send them out. There's always a chance that you'll go through a tunnel or something like that, and therefore it can't send it. So this buffering and everything else, that's something MQTT is very good for. But MQTT is not very good in scaling for user messages, and it's not very good in processing the messages. So it forwards them typically to Kafka directly or indirectly. All these different sensors, all these different Kafka sensors, they're all working around and producing huge amounts of data, which most likely not winds up in Kafka. directly connected to the internet. I've dealt with companies, retail processes that don't bother with the database anymore. Everything is microservices, and they're all connected via Kafka. So the first service coming in, when you type in your filling your shopping cart and type in the order, will wind up in a Kafka topic and will then be processed by the microservices coming on. Or simply streaming applications that go on, read messages from one topic or a set of topics, process them, and then write them back into another set of topics. And then they might wind up then afterwards in the data sink. The connection, the data pulled out from some sources, be it a database or written back, is often done with the help of connectors. So one of the parts of the Kafka architecture is this concept of Kafka Connect, which is a generalized form of pulling data out as a source or writing it away as a sink. And there are hundreds, literally hundreds of connectors available for all kinds of different sources. Many of them are maintained directly by Confluent that help you to move this data out. They're configured simply with a JSON file. So you can write an ETL application by pulling data out, by simply writing a JSON file that describes, I want to pull data out of this particular database. Often through CDC, change data capture, so it reads actually a log file of a database, which is much faster, and then writes it to a data sink like Elasticsearch, for example, again, by writing a simple JSON file that describes that. And in between, the processing of data, well, the streaming application can also be defined through a simple file. You don't have to do any programming. But I'm getting ahead of myself. This is one of the last points. The standard interface to Kafka is a simple producer-consumer. There is also an admin API to do things like creating topics or whatever, maintaining settings or something like that. But the main clients will produce and consume. These are primitives. They are simply writing to a topic or reading from a topic. If you want to do anything fancy on it or do any processing, then often you need to have a layer of abstraction on top of that that can describe what you want to do in more mathematical forms. Streaming API, now it's available in Java 8 as well, originally in Scala, in other languages as well, is a common way of describing that. You're basically viewing the data coming in as an endless tape and then run some operations on it, like filtering them out, modeling them from one form to the other, or mapping them from one form to the other, grouping them together in some shape or form, and so on. To describe that, the Kafka community has built these Kafka streams on top of the producers and consumers. And often these involve stateful operations. So while producers and consumers are stateless, they just look at each individual message. The streaming application can also have stateful applications like grouping data together, counting them over a certain period of time, and so on. And for that, it uses a state store. The state store is implemented using RocksDB, which is a C++ library embedded in Java. It actually uses a local cache as well. It dumps data to disk. Just gives the illusion of infinite memory, but in reality, it's dumped to disk. And it's also, if chosen, so written back to a Kafka topic, which kind of is a backup in case you lose that node on which the your streaming API runs. You can simply rerun it again from that particular topic. On top of all this sits KSQL, or as it's now known as Sql Db. This is something that Confluent has built, and it is a SQL-like language that enables you to define this streaming operations in this language. So you don't have to do programming. The streaming API is available on the JVM, so Java or Scala typically. You can use other languages as well that are available on JVM, but these are the two common ones. KSQL is simple text sent to KSQL service as a REST interface you send a message to as a JSON file. So with that, you can do many operations that the streaming API can do, from simple filtering data or mapping them from one shapeform to the other, to quite complex operations where you do windowing processing or something like this. With KSQL, you can do the transformation without writing a single line of code. So you can pull data in, as in the picture before, from a database using a simple JSON file, process them with KSQL, again with a simple file, and then send them back to, or send them out onto the store with another simple JSON file. You've written a whole application, and there are many applications like this out there without writing a single line of code. But of course, if you want to do something more complex, you probably drop down a streaming API and write streaming applications. And if it's really, really, really complex, or if it's a very simple use case, but you just want to just simply write data from one place or read data from another place, then you might fall down to producers and consumers, which are also available in different languages. There's a C library called libapache Kafka, on which based there are Python implementations, C# implementations, Go implementations, JavaScript, and all kinds of other languages as well. So with that, you can then simply produce and consume. Good. So, in summary, what is Kafka? It's an immutable log. It is highly scalable. We have systems, or I know of systems that can deal with hundreds of megabytes a second, something like pushing data with very low latency as well. It is distributed over typically a large cluster where we replicate the data multiple times, and fault tolerant in the form that a broker can go down, or even the consumer can go down in the consumer group without you losing your services and without losing any data. Kafka can act as a simple publish-subscribe queue. Not 100% because we don't ever delete messages, so multiple clients can pick message up. It is designed to be a distributed event streaming architecture, data in motion, as we call it now in marketing. It can be used as a database, and people do that as well. So, getting to this point, that's quick. There are a bunch of free books available. The Kafka Definitive Guide is now out in version 2, which you can download as a PDF from our website. Martin Kleppmann is a researcher at Cambridge University who has thought a lot about distributed systems. He's got quite a few books out there, and this Making Sense of Stream Processing is one of them. It's definitely worth taking a look at. Jay Krebs is the CEO of Confluent. He originally wrote this book out of logs, which the ideas of which are the basis for Kafka. So I have not personally looked at that book yet, but I hear it's very good to read. And finally, Ben Stopford, Designing Event-Driven Systems. This is a small book, but it's very dense with information. Ben Stopford is now the head of the Octo, so the office of the CTO, effectively acting CTO of Confluent. And you often see them presenting at the various conferences as well. So here's the QR code if you want to look at that, or simply follow that link if you want to get access to these books in PDF format. All you have to do is leave your information. And with that, thank you very much for your attention.
Okay. Sven, thank you very much for the great portion of knowledge. We have 2 questions regarding your presentation. So if we can answer, the first question is asked by Mr. Gamon1. So the question is even number broker not a problem for Kafka cluster in a context of picking up a controller? I'm not talking about leader of partition, but controller of a cluster.
It doesn't matter how many brokers there are for it to become a controller. Controller is simply picked as the first broker that comes up or it's awake and talks to zookeeper and says, I want to be the controller. It just has to be, say one controller in there, but the quorum based is done via the zookeeper. So zookeeper, that has to have the quorum in there with the right numbers. How many brokers are involved makes no difference because we only have one single controller in that case.
Okay. Thank you very much. Mr. Gamoni, I hope you answered your question. Then we have another one, which is asked by Cezary Michalczyk. In order to elect a leader, more than half must agree on a value, and that can, but theoretically doesn't have to, be not possible with an even number. If I can understand it correctly, is it right?
So there's a in order to qualify to become a leader of a partition, you need to have all the data available. So you have to be in the ISR list. There is a limited number of brokers who are in that ISR list, because typically you have a replication factor of 3 or something in the order of in that. So there are not that many to pick from in the first place. But the controller has a list of eligible leaders available, and then simply looks to the first one on the list and picks that up. It tries, if I'm not mistaken, I looked at the code in detail, to keep a balance so that a broker is not overloaded, but suddenly inheriting all the leaderships from all the other partitions together. But in principle, that is the concept set. So there are not that many. Even if you have a cluster of 20 brokers, with a replication factor of 3, there are only 3 particular brokers for a particular partition that are eligible. One of them is the leader by default. That's the static one we chose when we created the topic. And the other 2 have to be in the ISR list to be eligible. So quite a few times it might actually be that the third broker hasn't picked up all the data yet. So there's only one to choose from to pick up the ISR list. So there's nothing to do with the number of elements that we have in there. It's simply a queue, and we pick the next one that is available. And the other ones would typically pick up within a short period of time, a few milliseconds or maybe a second, something like that, to pick up the missing data that we have in there, and then rejoin the ISR list. So there's a lot of queuing and going with the brokers come in the ISR list, and then they're hanging behind the watermark of messages coming in, and then they're rejoining again, and so on. So it's quite a lot of traffic going on in that particular case. But it is very quick, and typically as a producer or a consumer, you don't notice that. I've demonstrated this many times by having a cluster set up where I on purpose switch particular brokers off. They know they're in leadership for things, and then just keep the producer consumer. They don't even stop. They just continue to work with that because it swaps over so quickly.
Okay. Sven, thank you very much for your answer. So guys, I would like to remind you that if you have any questions, please don't hesitate to ask them as a comment, because after the second presentation, we will have a small Q&A session. So there will be time to answer all your questions then you will have. So now we have a small break, like 3 or 5 minutes break, and then we'll start with the next presentation by Pere Urbón-Bayes. He's also working for Confluent, and he will talk about Kafka self-service operations. Sven, thank you very much.
You're very welcome. My pleasure.
Yeah, and we'll meet again during the Q&A session. And now we have a small break, and we'll be back after a couple of minutes. Okay. Welcome back after a short break. Before we start the second presentation, I would like to remind you that you can ask questions as a comment. Also, if you don't, for example, have a time, you can also write down and subscribe just to get the link to the recording of today's meetup. So you can just leave us your email and we will send you the link to today meetup. Okay, so now we are starting the second presentation. Welcome Pere Urbón-Bayes, who is also working for Confluent. Hello, Pere.
Hi. Does it work?
Yes, we can hear you. Everything works fine. Okay, so we are not delaying. We are starting now. So, Pere, the mic is yours. Please start.
Thank you. So, yeah, I am Pere, and as already been told, I work with Sven in the same team. This means we work with customers of Confluent who are deploying Confluent platform. And part of the deployment of Confluent platform is basically how do I implement or bring a little bit of the philosophy of DevOps into the tooling. And this is actually the motivation of this tool, of this presentation. Yeah, it's the experience of the journey across different customers and different experiences that I had in the past on how to bring a little bit of autonomy to Confluent platform, aka Kafka. Yep. So that's the boring part of the presentation. Who I am. As I said, I'm already a veteran in the industry, working for more than 15 years, nearly 20 in the job. In proud Berliner since 2011, but as you will notice from my accent, I'm not German, so I'm born and raised in Barcelona, in Catalonia. So, like one of my good colleagues says, always start with the why. So why are we doing this? What is the motivation? I'm sure if you ask yourself, well, a few of these questions all might end up with a very similar answer. What do you recall from the best team you have ever been working at? What do you think keeps teams or give teams a high level of motivation? These are questions that are very important because at the end, let's be honest, we stay at work a lot of hours. And to get the best out of that, it have not to be a torture. It have to be like a good place, and good teams are teams that actually feel these answers properly. There was this book called Drive, yeah, by Daniel H. Pink, who actually defined these three properties to answer the previous question: autonomy, mastery, and purpose. What does it really mean? It means basically have the option to self-solve my problems. I can get better at what I do, and I have a purpose. A process or a tool like what I'm going to present today, it actually tries to answer or give us help for the first two: how to provide people with autonomy, basically to allow them to solve their own problems, so they can focus on mastery, yeah, and they don't have to do boring tasks in Kafka every other day. So how do we get this with Confluent platform? Or Confluent in general, because it works with Confluent Cloud as well. What are the common questions that someone asks when it starts to deploy Kafka, Confluent platform on-prem, Confluent Cloud, etc.? Yes, a user, a project comes to me and tells me, I need topic. I need to create topic with a given configuration. How do I do it? You're working in a small startup with 10 people, no problem. But when you are working in a bigger organization, this has to have a certain order, or the thing is going to become like more unmanageable. How do I create access control? ACLs in Kafka, role-based access control in Confluent platform, etc. Or how do I manage schemas for the topics? How do I manage connectors? How do I manage SQL queries that Sven was talking earlier? Yeah? So basically, how do I manage the deployment of artifact and necessary configurations in Kafka? Usually, this kind of process and discussion involve different teams, from development to operations to security and to audit. I'm not joking when I say that for some teams, requesting a topic, it implies opening a Jira ticket. Yeah, so it implies going to Jira project, creating Jira ticket, then Jira ticket needs to go to planning, assign it to a sprint, etc., etc. So they get their topic or their ACLs basically after, I was going to say 3 months, but after a very long time. Yeah. Other teams actually work even worse, work via email. Yeah. Send an email to the operations team and let's pray to Santa Claus that this topic is being created, actually without error, etc., etc. So what we're trying to do here is provide an answer or a process to make this structure. And basically don't having to follow Jira or email. That doesn't work. So how do we solve this methodologically? As I said, the common questions for Kafka operations. I want to create topic. I want to give it a certain number of partition. I want to give it a certain configuration. I want to, or I need to deploy an application with certain rules, yeah? Or I need to create a service account. Basically, how do I make this boring, or how do I automate this boring administrative task that take a lot of time and that can, that are basically no fun at all to do, but they are required. You need to do them. For example, how do I rotate? No, it's not the case of this, but how do I rotate certificates automatically every now and then? Yeah. So these are common questions for Kafka day-to-day operation. As I said, some teams send email. Please, dear operator of hell, can you create a service account? Or can you create a topic with a given configuration? This causes frustration. Yeah, a lot of frustration, because it's either forgotten, it's lost, it's not done correctly, and you get your topic 3 months after. Or maybe some teams, and actually I've seen this in practice, both examples, request Jira ticket. Please create a Jira ticket. You're going to put it in the backlog. And, maybe if we are feeling well, we are going to create you the topic. Yeah? It creates frustration. As a team, what I want, as a developer team, what I want is to solve my own problem. I want to go to somewhere, say topic, or ACL, or literally anything I need, and provision that for me. This does not mean to have permission for anything, but it means that I'm able to solve my own or request my own resources in Kafka. Basically allowing me to move faster without having unnecessary bureaucracy in between. Another thing, it's important, as we mentioned, are topics. But if you have a little bit of experience with Kafka, it has a lot of configuration. You can put retention, you can put number of partition, number of replicas, you can put segment size, you can put compressions, you can put a lot of things. So one thing that the tool that I'm going to show you guys today uses is the concept of abstraction. So whenever we create topic, or we create actually anything in that system, it allows you to have not to know these things. so that you, as a developer, as an operator, can say, or an architect, my cluster has 3 categories. Yeah, silver, gold, blah blah blah. Yeah, and then you, as a user, as a developer, you can only have to say, okay, this topic is plan silver, this topic is plan gold. Yeah, and everything magically creates for you. I don't know if this is something that you know, but this was actually a very big hit when I was a kid back in Spain. Yeah, so it's like a Karate Kid, the movie. When, or like common source of trouble about any kind of operations work is not having automation. Yeah. Because we as humans are not very good at not making mistakes. We as humans will make mistake, will cause trouble. So I've seen times when people create 48, no, not 48, it was 98 partition in Kafka. That if you know, that's like not for everyone, yeah? Or people put unreasonable retention when you are not using tiered storage. And then disk fill up, yeah? So what's the story of this is automate everything. So part of this tool, or the benefit of this tool, is to give you an automation for that process. So you don't have to worry about basically filling in unnecessary processes or tasks for that. And if you happen to work for a highly regulated environment where you have to do change management, yeah, you have to have a list of who changed what and when for basically being PCI compliant. This will help you as well. Basically bringing the best of both worlds. Yeah, you can have PCI compliant with change management, and you can have automation. So yeah, you can focus on scaling. You can focus on happier problems than just creating topic and configuration. And even better. So if you have some experience with Kafka, you know that when you define things in Kafka, it's very low level. So you actually worry about segment size. That doesn't make any sense to worry about that. Or you define ACL for operation describe, yeah? Or describe config. Yeah? The objective of this tool is to have a description, to be declarative, yeah? A declaration of how do I want my cluster to look like. Yeah? And then allow someone else to basically say how or do the necessary changes for that system to work. Yeah, I find this much better than other approaches, more imperative, because it doesn't force you to have a lot of knowledge, yeah, or more detailed knowledge of the system, that it's sometimes unnecessary. So for example, if you have used the Terraform provider for Apache Kafka, or like even the CLI tool, yeah, it's low level, yeah. So that's why I pick up when I created this tool declarative method, yeah. So basically, among all these things, how do you bring autonomy and self-service to Kafka? We want and need a way for developers to describe what they need. We need a system that interprets the wishes of the user and automatically decides in the target platform what has to do. And we need to basically reduce unnecessary boilerplate interactions so everyone can focus on getting their job done. So for this, long time ago, in engagement after engagement, seeing people struggle with this thing, I created a tool that was called back then Kafka Topology Builder. but you cannot use Kafka as a part of a tool name because it doesn't play well with Apache Foundation naming convention. So now it's called JuliOps, and I will actually make an ask to the audience. Does anybody know why it's called Julie? There is no prize because I cannot send you a beer or chocolate, yeah. But let's see if you guys know why it's called Julie, yeah. In order to help bring GitOps to automate these processes and being declarative, centralized, self-service for Kafka operation. Why GitOps? Because it's bloody simple. I can have in Git my description, and I can then use either operator shell in Kubernetes or a CI/CD solution of choice to deploy these changes into Kafka. So how this usually works? You have either developers or operators as personas. You store your descriptions in Git server. I've deployed this system with GitHub, with GitLab, with literally everything that speaks Git, yeah? And that has webhooks. Then you have an pipeline, a CI/CD pipeline, that is basically taking out this data or this description from Git and applying it to Kafka. Yeah? Not only Kafka, can be Confluent role-based access control, or schema registry, or Kafka Connect, or KSQL, etc. Yeah? Over the years, it has been going evolving. But what's the trick? We want this process to be verifiable, yeah? So that people can have checks, validation, yeah, can have a kind of policy for these changes. For example, I will allow everyone to have between 1 and 12 partition. If they need more than 12 partition, they have to ask permission, for example, yeah. So the normal process for this tooling is to have one or multiple Git repositories where you store these descriptions, to do a pull request to change these files, yeah. And this pull request is validated. Does it make sense? Does it not make sense? You can do this with automation within JuliOps, or you can do this as well as a human being, yeah. Then you approve, it's merged to master, and the merge to master triggers CI/CD pipeline to do all the necessary changes. So at the end, we actually achieve continuous delivery of changes to Apache Kafka and Confluent in general, multi-tenancy out of the box, because the tool allows you to have multi-tenancy out of the box. Every change is documented, so you have change management, it's declarative, and it provides you with autonomy. I just was told this week that one of the biggest banks in Europe is deploying this solution for all their Kafka usage right now. So what do you get if you use this tool? You get what I said before, CI/CD practice. To get a way to do changes in Confluent on-prem or Confluent Cloud, yeah, or Apache Kafka. You do management of topic for creation, deletion, update of configuration values, yeah. Out of the box, multi-tenancy setup, so you don't have to do anything. Yeah, don't be shy to ask questions. It's actually very boring to only talk, yeah. So it's good to have ping pong at the end. So you have a way to do namespacing so have multi-tenancy. You have full automation for creation of access control rules. What it basically means, if you have some experience with Kafka, that for deploying a certain application, you need usually a long list of ACLs or roles in Airbag. So what this gives you is a way to say, okay, I want to deploy this application. here are the configuration properties. Please create all ACLs for me. Yeah, I don't want to know. Way to create ACL for platform deployment, schema registry, connects, control centers, etc. Schema management. It's not written here, but latest version can do deployment of connectors, can do deployment of SQL queries, and what is very cool that I'm going to show you later, can do management of metadata. Yeah, so you can actually annotate topics with metadata. All these features come to you magically with doing create, delete, update, etc. when required. This is some links with information to actually a little bit older, but there is redirection, so it's going to work for the tooling. But is JuliOps the only thing that you guys have? No. Obviously, I made JuliOps because I think it's a better option to solve this problem that we spoke about. But you can do, for example, using Terraform with Terraform provider. Or you can, if you are deploying with containers, with Kubernetes, you can do something that's actually pretty cool. That's called open service brokers. With open service brokers, you have a catalog of things that you need. It's actually a concept that comes from it's actually a concept that comes from oh, I forgot the name. From Tanzu, yeah. So from Cloud Foundry, yeah. Now, sorry, I'm getting older and I forget names right now. Where you have an API, so this is fully available in Kubernetes right now, so it's not like something from Cloud Foundry, but it's actually born in with Cloud Foundry deployment, where you have an API, you have a catalog of what you offer, and then you have some kind of provisioners, yeah. And actually, we did this work. We created an open service broker component for one of our customers in Germany. And the idea is that from Kubernetes, you can say, please give me a topic. Please give me a configuration or give me an ACL. Yeah? And then the catalog knows what he offers, knows where to ask for it, and give it to you back, including secret management and all the magic. So if you are doing things in Kubernetes, that's a lovely pattern to use and actually pretty cool, because you can do not only Kafka, but you can do MySQLs, you can do Postgres, you can do resources in AWS or GCP. So it's like lovely pattern. That's actually from Cloud Foundry example that I used a while ago, how this works. Yeah, so you do please create service, Kafka of type gold, yeah, and topic name T1, yeah. So you ask a controller will talk to the service that you implemented and deployed for the service broker, will create topic and will respond back, yeah. And basically what this will do is request this topic. And then what you do is a binding, yeah. You say now this belongs to that app, yeah. And magically this bind request sets ACL or API key for Confluent Cloud and give all these secrets back via environment variable set to your application in Kubernetes. Basically, making a very easy way and very self-service way to provision your own resources. For example, if you're a platform team, you can create one of these thingies, or use one of the multiple that are public on the internet, and and basically build your get your users happier because they can solve their own problem, and you can basically create this for yourself and focus on funnier things to do, or in fixing Kubernetes errors. This is a list of 3 or 4, well-known service brokers. You have for Mongo, for Cassandra, one from Kafka, that's from Cloud Foundry people. And the last one is the one that my colleague Benedict Linse, who was the developer who did this service broker for our customer, did, yeah. And it's, if you are doing it in Kubernetes, it's actually very cool way to do that. Actually, for my opinion, much better than operator pattern, but that would strike a philosophical question. So now comes the really interesting part of talk, the minions of the demo. So for this, I have, so for the ones that doesn't know, I'm gonna use Confluent Cloud. Confluent Cloud is a cloud offering from Confluent, yeah? Basically, it's an easy way for me to create a cluster and don't have to worry about things, yeah? Just logging into the system so I can show you the UI. Yeah, so I have this cluster here. That's one of the simplest clusters that it's offered, but you know, it will allow me to basically show you guys the result. See, there is no topic here. Yeah. So we are gonna then see here the things. So in make this bigger so it's visible. We can see that I prepared this before. This is Confluent CLI tool. Yeah, there is no topic here. There is no ACL. Yeah. So there is no topic, no ACL. Yeah. What we are going to use today is this tool. It's JuliOps. Yeah. Again, I'm repeating the question. Does anybody knows why it's called Julie? Don't be shy. It's actually a fun answer. It's available for you as a Meet license. Yeah. So basically means do whatever you want, contribute. Yeah. But please don't claim that JuliOps is yours. Yeah? JuliOps is made by a long list of contributors. Look, sorry guys, I have my son over here who has a very important thing to tell me. ¿Set cartas?
No. Sí,
Estic fent una presentació. Estic fent una presentació. Look. Déu. Sorry guys. So there is a long list of contributors. This is me, yeah. Funny thing is there is contributors from Confluent and from outside Confluent, yeah. These two gentlemen are two gentlemen who contributed a lot of code. They are two guys from Norway who love the tool and did a lot of work here. He doesn't work for us. He's a guy from New Zealand. One colleague from Germany that doesn't work with us, but I know him from a long time. You see here Sven, yeah. So even Sven has contributed things to JuliOps. One nice folk from France, but again, no Confluent employee. So it works a lot with a lot of contributions. If you want to use this tool, yeah, as I said, Meet license, yeah, it's offered to you in multiple, let's go here to the releases, yeah, it's offered to you in multiple forms. So you can get this either file jar thing and, be my guest. You can get it from Docker Hub as a Docker image or as a Debian package, RPM package, etc. Yeah. It likes to have some documentation. Again, I apologize myself because documentation is not the best thing ever here. It has as well here some descriptions, yeah, of what it do, yeah. It's a CLI tool at the end, even if it's done with Java, yeah. And here you have a long list of examples, yeah. Cool things of JuliOps that I want to show. So this one, for example, yeah. I'm gonna make this bigger. So this is the description. This is the descriptor. You can define, when you create multi-tenant project or a Kafka project, you will define a topic naming convention. Basically how you want your names to be, your topic names to be, yeah? So because JuliOps is opinionated, it will have a key, yeah, before the projects, yeah? This is the context. Basically a context is a container of projects, yeah? Then a list of projects, yeah, who are a container of topics. Every project will have a list of permissions, either consumer with their principal, producer, Kafka stream, connectors, etc. Yeah? And a list of topic. In topic, you can give it a name, and then it will use the previous properties, project, context, etc., to build the full name to allow multi-tenancy. In topic, you can define multiple configurations from replication factors to data types, etc. But actually, one cool thing that I like a lot from the system is possibility to define metadata. So you can have here metadata and say, okay, this topic is from sales or this department, or this application is from that system, and that's the contact of that system. So then what many of the customers I work with do is use this as a way to discover who owns a certain topic, or what are the topics that hold data for sales, yeah? Basically allowing them to annotate topics. So this is very cool thing, yeah? So this metadata, very cool thing. And you can do in topics, in permissions, yeah? You can do everywhere. Here you have an example of how you can handle schemas, yeah? You have a directory, and then you pass the ABSC, and you will create, in JuliOps will create a schema for you. Another cool feature of JuliOps is it allows you to define plans. If you remember earlier, we talked about the option in JuliOps to don't have to write too much, to live on abstraction, yeah? So here we see like plan silver or plan gold, yeah, in this example. So what this will do is it will fetch the a previously passed configuration name, yeah? We failed gold and silver, and we'll use this configuration, yeah, as a baseline for that, yeah? So basically it's a way to inject a specific configuration, allowing the users not to focus on that topic, yeah? And you to set up a specific thing. Last but not least, in Julie, yeah, you can create connector. So you can actually define a list of artifacts, yeah, for connectors, a same thing for KSQL, yeah, and create them for you, yeah. So you can automate creation of connector. Same thing for KSQL query, yeah. And last but not least, you can define roles, yeah. So if the previous permission were not like cool for you, now you can actually create your own, yeah, and define permission for a specific application. But after talking way too much, let me show you guys, yeah, what we're going to do now. So basically, we're going to use a previously created example configuration like this, yeah. This is a way to use JuliOps to connect to Confluent Cloud, yeah. Again, I'm using Confluent Cloud because it's a very easy way to basically run something, yeah. So what I'm going to do here, I'm going to go back to the shell. This is not like the usual way of running JuliOps, but it's kind of the easiest way for me right now because I have the full project here. So we're basically going to do like this, yeah? Going to pass the broker, yeah? Going to pass some configuration to actually being able to access that broker, yeah? And very small topology, so we'll create the resources, yeah? Okay, let me see that I have nothing created before, yeah? So let's execute this. So, okay, sorry, because it's demo effect, it's trying to have error at some place. Service name. What is still complaining right now? Oh, the user account. The user account is already there and it doesn't allow to delete, yeah. So let me go here. Sorry. Oh, why it's using cloud? With the schema, cloud, yeah. Let's do like this and see if this works. It's a demo effect. Yeah, I basically disabled the check for users. Yeah, so in JuliOps you can manage as well a service account. So this was having no proper permission. Yeah. So basically this has created a bunch of resources. Yeah. Now if we check for Kafka ACL list, it has created some ACL. Yeah. And if I list the list of topic, it has created some topic. So what is the file that I use here is this one. Yeah. I can make this bigger. So I have context OLTP, then project foo, and a list of topics, foo abro, bar JSON, Z, project bar, etc., etc. And then a user here. Yeah. So this is what you see here. This is oltp.foo.bar and the different topics created here. If now, for example, I take out this whole bar thingy, yeah, and I only let project foo, and I execute tool again, and now I list topic again, we see that now here there is no bar. Yeah, that's because I allowed the tool to delete. Yeah, but delete it is scary. But you know, if we do the right thing, delete is not a bad thing. Yeah. So another thing that I can do is instead of allowing delete, yeah, now I will not allow delete. Yeah? So I will not allow delete. So now if I go here and now I create, I take out project bar from here, yeah, and I run tool again. We see that topic bar is still here. Yeah? But what's the trick here? So Julie requires a state. So there is a file called cluster state. Yeah, that it has all the state here. So it basically has a representation. Carai, estic fent una presentació, carinyo. Sorry, guys. Now my daughter, estic fent una presentació, carinyo. Després m'ho ensenyes.
Però mira que xulo.
És molt xulo. És molt xulo. Carai, no puc parlar ara. That's the beauty of having kids at home. They appear. Yeah. So this state is actually the one that keeps information of what has been created and how the cluster looks like. Yeah. Nice thing of JuliOps is you don't only need this thing, but you can actually as well take information from cluster. So if you don't want the state to be kept in local storage, either a file, Kafka topic, Redis database, S3, GCP, etc., yeah, you can pull directly from cluster. Yeah. So as I said, that's the part of the presentation. You have here, like let's go here. You have here example how to use it with Confluent Cloud. Yeah. If now we go to the Confluent Cloud, we see that these topics are here. Yeah. We cannot see ACLs in UI, but yeah, we see it from CLI. Yeah, that ACLs are here created. Yeah. Yeah, and you see. A mi hijo y a mi hija. Los dos vienen a visitarme. No joke. Once I did a presentation in Mallorca with my oldest. Yeah, he was running around, and I did presentation about Kafka in Mallorca. Yeah, so you have here like the topics created, and basically all this process is either integrated through CI/CD or integrated through through shell operator. Cool things that you have in this bunch of reports here. Yeah. So you have a demo that right now doesn't work for me because I basically destroy my Jenkins instance. But this is an old demo that I used to do to do the same thing with Jenkins. Yeah, building new one with GitHub Actions. Here you can see that there is a lot of pull requests where people did some comments and then did the merge into production, into master. And from master, there was the change or the application into the topic, as we have done here, basically manually. You see from JuliOps directory that you have here as well few Docker instances to play with that, some with Kerberos, etc. So it will cover basically your normal usage in Kafka. And you get some here, some example scripts, how to do a few things, So that's mostly the presentation and the demo. It's time for questions.
Okay. So thank you very much, Pere. And we have one question from Cezary Michalczyk. Could you please present how topology, YML file, and the config looks like, which you use in the Julie action step configuration?
Okay, the direct configuration I can really give you, Cezary, because it includes secrets to access my Confluent Cloud instance. Sorry for that, but it's actually like this, So you have here a full example where you only need to fill blanks, like in this file from here, I will put in chat, So, well, I will put somewhere, so hopefully you can
want
copy
to
this.
Share your screen again?
I'm sharing my screen, isn't it?
No. Okay.
Oh,
no.
Sorry, I didn't say that. I apologize.
Okay.
So here is like fill blanks, So you have this template. Copy schema server URL, copy secret for schema registry, Copy everything you need. Copy secret key for API key, etc., etc. I was not using this provider, Cloud provider. I was using something called hybrid provider because lately I use a lot of private link and I need to use a hybrid provider, but here just fill blanks and enjoy.
Okay.
What's the deal? So here is the thingy, the configuration, and then pick up any topology from here, I use this one because it's small, so it allows me not to, worry a lot. But you have here like full things of one with plans, one for airbag, one that's short, one that has KSQL, and one that has everything, So one that has the whole thing, So, like every open source tool, guys, it lacks a lot of documentation, So please bear with me. It's on best effort, any contribution, any improvements, everything is very much welcome. So that's why I shared at the beginning that this tool is only possible because 33 people decided to help out,
Okay. Thank you very much. Yes, please continue.
No, please go ahead.
Okay, we have another question. What is reasonable number of partitions per topic? Let's say cluster has 3 brokers, but just one disk connected to each broker. So it's not possible to spread partitions among disks.
Mr. Gammon 1.
Yes, exactly.
That's $1 million question, So it is like Harry Potter, giving you an answer. I will say 2 things to answer your question. First, you usually don't have a single disk per broker, You have at least 2 disks. One for the operating system, one for the topic, for the logs in Kafka. Why? Because you want that there is no I/O contention. You want that the process of writing into logs, into real Kafka data, it's separated from the rest, And now going to the initial part of the question, what's the magic number for partition? partition is unit of scalability. Yeah, in Kafka, either for writing more data, yeah, or for reading more in parallel. Yeah, but you will have, of course, disk for OS, disk for logs, disk for application. Sorry, I had to say the thing about the disk, Mr. Gammon, because like it's not the first time that someone asked me that question. And now number of partition, yeah. So it's magic number. It's very hard to say an exact number because it depends on your requirements, yeah, and it depends on your cluster. What I would say is, if someone asks you more than 12 partition for a topic, it's generally a bad idea. Yeah, it has to be very well explained. Why? Because in Kafka, when you have too much partition, your tail latency will increase. Yeah, because Kafka is not only the use of partition.
Okay.
2000. Oh yeah. Well, but this depends. You can have brokers or very small. You can have brokers that are very big. Yeah. So what I was trying to say is, and events could be of different size. Could be events. I've seen people sending events of 10 megabytes. No joke. Yeah. Or people sending events of a few cars. So it's all about writing faster. Yeah. More partition. It's all about reading faster. Yeah. And it's all about saturating your network. Yeah. So getting as much traffic as possible within your network, but without limit. Yeah. Because if you do it too much, you're going to affect your tail latency. Yeah. Mm-hmm. So my rule of thumbs for work, and for the project I work with, it's if it's till 12, yeah, till 12 partition, no big discussion. Yeah. If it's more than 12 partition, requires discussion and argumentation. Yeah. So it requires to do calculation of why more than 12 partition. Yeah?
Thank you very much, Pere.
Sorry for the long explanation, guys. It's like a concept.
We have more questions from Mr. Gammon. Another one is it possible to have a split brain within Kafka cluster? What scenarios could be a reason of that?
Mr. Gammon, I'm starting to like you. You put complex question into the chat, yeah? This is good question. The last time I saw a split brain in Kafka, it was end of 2016. Yeah? So I don't say it's not impossible to have, but right now you have to really screw it up to have a split brain in Kafka. Yeah? There are a lot of protection, especially in the Zookeeper area. Zookeeper is very mature. Just remember, Zookeeper is like your grandma. So a good friend, a good colleague former colleague of mine right now used to say, Zookeeper is like a grandmother. Yeah, I don't know Polish grandmother, but I can guess it's like any grandmother in Europe, yeah, or in the world. They are awesome. They are the ones that cook the best, yeah. But you have to take a lot of care of them, yeah, because they are older, yeah. So Zookeeper is the same thing.
Okay.
With normal configuration, if you go to our Ansible project, for example, sorry, if you go to Ansible project, yeah, you go to on CP Ansible, or you go to any of our example deployments, it is really, really hard to do that. If you enter a situation with split braining in Kafka, yeah, it could happen if there are more than one. So if you are working in, for example, in 2 data centers, yeah, and didn't put enough zookeepers, yeah, this could happen, a kind of a split brain scenario where your zookeeper gets unhappy, yeah. Sorry, I don't know if I asked, but this is really another complex topic to explain, yeah.
It's a very complex topic, but typically this happens in a 2 data center setup.
Yeah,
that's why we always recommend, if you can, to make it a 3 data center setup, because then the quorum is always guaranteed. Even if you lose one single data center, you can continue with that. The split brain that we're fearing in Kafka cluster is if you have 2 controllers. If you have 2 controllers, then it'll assign leadership to partitions in 2 different places, and afterwards you can't bring it back together.
Have you actually seen any lately?
Sorry, what are you saying?
have you seen any split brain lately?
No.
That's what I'm saying.
There have been bugs like this 3 or 4 years ago, but they have long been extinguished. No, I haven't had situations of that at all.
The only point that I can see split brain scenario or kind of a split brain scenario is if you are in 2 data center and have three zookeeper, yeah, or so that you don't work with hierarchical mode in zookeeper. That's the only point I can see similarities to
with the correct configuration. You will get a situation where you, in a 2 data center scenario, where your brokers will simply stop to accept any new changes until you have reconfigured something. And what you need to reconfigure, we typically practice with the administrators of the system. We provide scripts, we provide runbooks, so that they can deal with that. There's a very clear signature of my data center is down, I can work, and I need to make some changes. Now, ever since 2001, of course, we have created multiple data centers. We have split the data of multiple data centers because you fear that one data center might be lost. Ever since then, I have not seen any data centers disappearing by themselves. Well, maybe with the exception of the one in Sydney when the wildfires were coming in. But they were taking all 3 of them out, so there's no real choice about that. But a scenario that they all talk about is a digger showing up in front of the data center and digging out the network cable in between, or a fire happening, or something like that happening. None of that's
sloppy network administrator.
What I have experienced is administrators going wild and changing the network configurations, either changing firewall rules or something like that, and suddenly taking the data center offline because they have misconfigured it. It creates more chaos than it resolves in reality. What we do is when we deploy, when Pere and I deploy these kind of clusters, we tend to recommend to do that in the cloud, like AWS or GCP or Azure, when typically spread over 3 availability zones. And here it is the administrators of those clouds will then guarantee that the services will stay up. And they know how to deal with that, and they don't fiddle around with the parameters as some of the overzealous administrators tend to do. Or simply use Confluent Cloud, which is spread by default over 3 data centers, and we take care of that as well.
Just a comment, Mr. Gammon, to your message. Yeah, the only thing I would change in your setup is put 2 more zookeeper. Yeah, you mentioned 3 AZ, 3 broker, 1 broker per AZ, and 1 zookeeper per AZ. Yeah, having 3 zookeeper is the minimum. If 1 zookeeper dies, you are in actually like a bigger alert than if you have 5 and 1 dies. Yeah.
Okay, thank you very much. We have smoothly started the Q&A session, and that's great because it's a very great discussion here that we have here. Another question is also from Mr. Gammon. Is there any monitoring tool that would be more intelligent besides presenting metrics, would also give some advices or pieces of advice that we are going to meet some limits, for example?
Okay.
Just give me a second. I need to find the name so I say it properly. Just give me a second. I'm looking for the name of the nice ladies who do this. Schade.
Wen suchst du?
Just 1 second.
Not a problem. Take your time.
Oh, yeah. Sorry. So many names and I don't... Honeycomb. Now it's... So it's this thing from here. That's proper observability done like real thing. Yeah. So what is intelligent? Yeah. It's a complex word to say, but normal tools for monitoring, they are just pretty things to do dashboard. Yeah. They calculate some standard deviation, etc. So no. The other thing that I can that it's actually, but it's more tricky than that one. So Honeycomb is for me like the best one ever. There is a product from Elastic that's called Elastic Observability. Yeah. Mm-hmm. It is not exactly like Honeycomb because, like Honeycomb is just a full grown up system for doing that. But what Elastic does is you get a signal. Yeah. So you get a graphic with a function. Yeah. And it calculates outliers. So it tells you when a signal, it's basically not doing what it should be doing. Yeah. And that's the bit that brings intelligence. Based on my own experience, some tools or basically derivative of Prometheus say to do something called AI ops. Yeah. I still have to find one that does this properly and allows you to be intelligent in what should be an alert or not. Yeah.
Okay.
Not that it cannot happen, but the closer that it happened is what Elastic offers with basically time series analysis and outlier detection. Yeah, for the word intelligent. Yeah, but intelligent is it's overrated.
There's something else to add to that as well. So one of the typical things we see is that brokers get overloaded because the load is imbalanced. We have created topics in a static way. They were based on heuristic, where we basically just look at the number of topics that are, or partitions that are assigned to a particular broker, and then just go around robin and try to keep that even. But we don't know how busy these topics, how busy these partitions will be. It depends on key distribution. It depends on how busy these particular producers are writing into this topics and so on. So what we, Confluent, have done is we added the ability for the brokers to shift partitions around between the different brokers. So if you have a large cluster of many different brokers, you can move them automatically. So there's an automatic what's it called?
Self-balancing cluster.
Self-balancing cluster, thank you. There's a self-balancing cluster capability built into the Confluent server, which is kind of a superset of the Kafka broker, that automatically will shift this broker, these topics around, or these partitions around, and does it carefully because the some of these partitions are very busy. They have gigabytes, terabytes of data stored in them, and they don't want to simply copy them over to a different machine. So it does it in a throttled manner. So that's one possible way of how we can deal with the load imbalance. And often it is that load imbalance is the reason why a broker can't respond fast enough anymore. And in the worst case, it doesn't respond to Zookeeper anymore, and it's taking out of the whole load, and that causes a cascade. So we're trying to avoid that kind of thing. And some of them can be done automatically without you having to go monitoring and then add to that kind of thing. Cruise control is the way that LinkedIn did it themselves. So they have a humongous cluster that for a long time was the largest Kafka cluster out there. After all, they invented Kafka in the first place. And Google did this automatically beforehand for theirs. This is an open source tool that was shared. We took those lessons that learned from cruise control and expanded them for the Confluent cluster. That's what we do internally. Thank you. That's what we're doing internally as well in the Confluent Cloud. So that has this ability built in. And as a user, you simply go and dial up kind of a meta information we call the CQ, or Confluent Kafka unit, where you simply say, well, we need more space, we need more throughput, and then we create more brokers, bring them in, and then use the self-balancing capabilities of shifting the partitions around so that the whole overall cluster is balanced.
So to complement what Sven is saying, so we are moving from monitoring and observability, taking a look, what the hell is happening, to being more proactive and being you with health, So instead of looking at your health metric, going to doctor regularly and having your doctor check up on you, every now and then. What is the great thing of cruise control, self-financing clusters and all these things is they provide an initial step of self-healing. Yeah? Basically, possibility for Kafka cluster to correct his own issues. Yeah. I have to say one thing, guys. If you are starting with Kafka, that's not for you. Yeah. So running cruise control or running self-balancing Kafka, second one is much easier because it has way more abstractions, but it's not for beginner. Yeah. It requires you to have suffered a little bit some of the things. So I would totally recommend to start like learning the ropes, yeah. And then as soon as you are a little bit more comfortable with what can go wrong, start applying magic on top, yeah. Because these things feels like magic.
I'm running a training course at the moment in parallel for our partners. And part of the training course is to go through all the different kind of configurations, so you can set the Confluent server up, respect to security and setup and so on. And they learn this the hard way. We call it a boot camp for a reason. Part of that boot camp is to also understand how to secure your Confluent Cloud instance. And whenever I run this and then ask them after they've suffered 2.5 days already to configure Confluent Cloud on various kind of environments using our tooling, Ansible and so on, to get everything to run. And well, depending on how the experienced they are, many times they have done something similar, that they struggle more or less to build it up. But it always takes them a few hours to bring this thing done. And then I ask them to connect to Confluent Cloud, create a new instance, you create a new account, create a new instance, click on it, and then connect to that. And it takes them about 5 minutes. And the comment I always get from that point is then, we're just putting this on purpose right into this training course just to encourage people to use Confluent Cloud. But we claim to be the experts in Kafka. We've done it many times. Some of us are the people who originally created Kafka as well. We know the ins and outs of that, and we put an awful lot of effort in to build the Confluent Cloud. So more likely than not, this might be the better solution, and you can start it out for free. There's no paywall anymore. You can simply set up an account and try out the basic cluster. It's underneath shared with other people. So at a few clicks, and they have a running instance in which you can connect to that. It's a good way to learn about that. If you then decide, well, your data is actually confidential, or you need to have guarantee of no latency whatsoever, while the cloud provider is still a little bit away, something like that, then yeah, by all means, take those lessons learned and then put it in the cloud. But I find that the majority of our customers that we deal with these days, Pere and I are solutions architects, we're dealing with customers all the time, is that they are either looking at the cloud intensely already or have already migrated to the Confluent Cloud.
Yeah. So to complement a little bit what we were talking about monitoring, yeah, I shared the link here with this project, JMX Monitoring Stack. Yeah, it's not bringing your intelligence, yeah, but it's gonna bring you all the right metrics that you need to look for. Yeah. So if you look at this repo, there is directory with JMX Exporter, Prometheus, and Grafana. Yeah, this project is completely open source. So it's something that we created from the field at Confluent to not have to repeat the same story all the time. Yeah, so basically point customer, go here, read, copy, enjoy. Yeah. Okay. So please, guys, you know, like especially for the guy of the 1,000 question, this is something that you might enjoy. Yeah.
We also have a question regarding the metrics, the measures. What are key measures that we need to monitor to have healthy cluster besides CPU, memory, disk space, and heap usage?
Oh, yeah. There is one that some people don't like to monitor, but it's very important. Yeah. It's called under-replicated partition. Yeah. So some people will tell you, don't monitor that. It's just, you know, it's a canary. You know, if the canary is dead, it's no problem. We can get another canary in the shop, yeah? But it's a very good trigger to sense for health. Because if something gets fishy, 99% of time is going to show up as under replicated partition. Yeah. So if, for example, if you are doing a rolling upgrade, yeah, or literally anything happen, look at that. Whenever I see cluster that I go to customer with under replicated partition and they accept that number, I ask why. Yeah. Because it's always an indicator that something else can be happening. But that's for broker. There is the for Zookeeper, yeah. So sometimes in Zookeeper, there is the number of followers that are in sync, yeah. So in Zookeeper, if you have 5 Zookeeper and you only get 3 in sync, you are okay, but you're actually in bad situation because you get 2 that are not in sync, yeah. Telling you more metric to define health of cluster, it's gonna be like a story of a long time. But what I can point you is, apart from the repo that I just shared, where it's everything that you required, yeah, is to the link that I'm sharing right now in the chat. Yeah, this is the subset of the document. This is the subset of monitoring Kafka. Yeah, and you get all monitoring that it's important. Yeah, you get metrics, for example, like bytes in, bytes out, that does not give you health information, but will give you if a broker is overloaded. Yeah, you have one that it's very important for Kafka health, but it's not like a health. Yeah. It's number of partition. As we said before, as more partition, bigger the latency, yeah? So you want to control that. Yeah, it's, there's a lot of lists. So for example, I would say probably offline partition count, yeah? If partition is offline, you are probably in some degree of big trouble. So yeah, the list is quite big, yeah.
Okay.
Replication lag would be one that.
Yeah.
These are there's more a bit more advanced, but if you have a replication lag, then obviously producers will suffer, because if they're asking for access all, which is the default, then yeah, that's one of these things that you should look out for.
There is I cannot share here. Kafka operations, 1 second. Stories from the trenches. Lessons, yeah, here. No, this one not. I'm gonna look for a slide deck that I have it here, and I'm gonna share it as well as soon as I find it. Otherwise, look for on the internet for anatomy of a request, yeah. Or look for my talk at InfoShare, like a few years ago when there was no COVID. Yeah, look at my talk at InfoShare. If you guys have the slides published, it's there. This is slide that I'm saying.
Okay. We will try to find it out and put it in the comment, or just to send it as like a takeaway from the presentation.
Yeah. So why I'm mentioning this is there is anatomy of request. Yeah, and it complements what Sven is saying. So there are a lot of times, yeah, in Kafka request. So queue time, disk time, remote time, response time, etc. Yeah. Monitoring all these times, it's important, because if disk gets funny, IO time is going to increase. If network gets funny, replication time, what Sven was saying, is going to increase. Yeah. So no, literally a measure of health, but very, very, very valuable information.
Yeah. Okay. But you just mentioned, well, this last one on that one, and I think we have enough pointers about that. There are 2 thread pools, one for them for accepting network connections, and the other one for writing messages out from the buffers or onto disk. The network pool, thread pool, and the IO thread pool. Both of them should not be exhausted. If you're running out of threads in there, then you start blocking on CPU in context switches. So it is important to monitor those values and see that they have sufficient threads available that they can pick up new codes. Otherwise, you get latency by trying to connect and so on.
Okay, thank you very much. And we have last question. Let me find it, please. Just give me a second. Okay. Yes, this is the last question. Can you please describe how Kafka uses heap? What are golden rules to set XMX, XMS?
Oh, bigger than 7, 8 gigabyte? No. Don't do anything stupid like putting 64 gigabyte of heap size in Kafka.
Yeah, 6 gigabytes is the my limit, even for
6, 7, yeah. No, nothing bigger. It is just going to shoot yourself on the foot, yeah? So it's just going to shoot yourself on the foot.
This is because all you do is you delay the garbage collection. And when the garbage collection kicks in, then it actually becomes a measurable thing instead of just taking a couple of milliseconds or something like that. Now, having said this, in percentage of RAM, no. Follow Sven rule number 2, which is, Pere?
I don't remember. You have way too many rules, my friend.
No, I only have 5. Sven number 2, more RAM is always the right answer. RAM in the box. If you have a slot, fill it. But the broker itself should not run with typically more than 6 gigabytes heap, or maybe 8 at a stretch. It doesn't need that much memory. Yeah, what it needs is file system cache, because if you serve many different partitions out of that broker, many consumers reading from that, they want to read from cache. They don't ever want to go back to disk. Disk is slow, cache is fast.
Leave at least between 35 and 40%, or between 30 and 40% of RAM available for the operating system. Never, ever, in any machine, use more than 70, 75, of your RAM, because otherwise your system is going to start pagination, and that's something you don't want,
Okay.
So my rule is kind of 4-to-1. So 25% of max RAM.
Yeah, no bad.
So I configure my broker about 6 gigabyte RAM, and then have maybe 24, maybe 32 gigabyte RAM in total available on system for operating system and file system cache. And that is a reasonably good mixture. You typically find a very good response to that, and it'll never run out, and typically serve many partitions in parallel.
Think that Kafka was designed not to be in a huge box, was designed to be in a very small boxes, and many of them, So
Okay. So I think that we have run out of a question queue that we have. So I think that's it for today. So Sven, Per, thank you very much for your time, for the knowledge sharing, for your presentations. It was a great pleasure to have you with us today. Thank you very much, and maybe see you soon. And
always a pleasure. Thank you very much. You're very welcome.
A pleasure,
Okay, and thank you guys for watching us. Bye-bye. Thank you.
Goodbye.
Bye.